Hello everyone, this is the lecture on the Perceptron. So, uh, so today we will learn how to train a Perceptron, and uh, and we will learn about the most important steps in a learning project, and these steps will also be relevant for the other models we will study. So the first thing is that you have to take care of your training data. So you have to collect the data, or somebody collects the data for you. Typically, you have to clean the data, so there might be missing data, there might be outliers, and you have to decide what to do with these problems. Typically, there's also some pre-processing of the data. For example, normalization, that you subtract the mean and normalize the standard deviation to 1. So you find this in many books. It's also covered, I believe, in the lecture on KDD in detail, so we will not discuss these issues too much in this lecture. Then you typically define a class of learning models. So typically some mathematical function with some free parameters, so parameters you adapt based on the learning, on the training data and the learning process. Sometimes you have an outer loop where you also try to find a good model. I mean, for example, today we're covering Perceptron, but there are also other models. And it's not clear a priori which one is the best one. So then you select the cost function, which is a function of the data and the free parameters. And you define it in a way that a good model, so a model which has a good power to explain the training data, has a low cost. And then you do the learning, which is an optimization step. You try to find the best model in the class of learning models under consideration by a so-called learning algorithm. Typically, at least in the inner loop, it means the learning or the estimation of the optimal parameters in a model with a fixed structure. So typically, in the inner loop, you have a fixed structure and you learn the parameters, and then in an outer loop, you might also try to optimize the learning model and the structure of the learning model. So we are considering now a prototypical learning task, which is the classification of printed or handwritten digits. So for example, a zip code on a letter. So the application is, for example, the automatic reading of postal codes, or more general problem, OCR, optical character recognition. So here is an example on the top. In the first row, you see 10 examples of numbers from 1 to 0. And these are, let's say, machine generated, so they always have the same appearance. And so there are small images, in this case, I don't know, 5 rows and 3 columns each. And a learning machine typically likes to work with vectors. So you transform these digits into vectors. So for example, if we look at the 2 here, which is represented in the second row of the data matrix here, that starts with 1, 1, 1, 0, 0, 1. So you see it 1, 1, 1, 0, 0, 1. And here you see the other pixels. So in the same way, each digit here is transformed in one row in this learning matrix. And this is typically considered the input. And we also have to each pattern a target or an output, desired output. So the first one represents a 1, the second one a 2, and so on, and the last one represents a 0. So this is typically the form we transform our data into. So on the left side, sometimes it's called design matrix. So each row is an input vector. So it's a row, which is important. And the last column here says what the targets are of the corresponding training patterns. So the number of real inputs, so in this case these pixels here, the number is m in our notation, large M. The number of data points in the training data is large N, so you have n examples. And we add one column which only consists of 1. We don't always do that, but for many learning approaches, perceptron, linear classifier, and so on, this is mathematically very convenient. So the number of inputs is m plus 1, but we only have m real inputs, meaningful inputs. Now, the first one is always 1, so it doesn't give you any information. So in supervised learning, just to give you a little bit the mathematics, so we start with x. So x would be one of these input vectors, which is an element of the m-dimensional real space. Doesn't always have to be complete real space, but in general it is a real space, a number of real numbers. So this is an element in an m-dimensional vector space. Then we consider a function f, which maps an element of this m-dimensional space to a scalar. So we can also write a mapping from x to f of x, where x is an element of this m-dimensional space and y is a scalar. In general, we are interested in the expected value or expected output of some quantity y, which is accessible to measurement, given that we know x. So f of x typically represents this expected value. So this all becomes more real in the course of the lecture, so I hope you're not scared away by this mathematical introduction. Essentially, it's the mean. So if for example, x can be mapped to several outputs, we are interested to predict the mean of these outputs in general, not always. Typically, not always. So example 1, x represents a machine-generated written digit as an example, and y indicates if the digit is a 5, then y would be 1, or any other digit, then y would be 0. So we have only binary classes here. Then f of x can be either 0 or 1, since it is possible to classify machine-generated written digits perfectly. Typically, so if you consider a lot of different fonts, you can try and classify all these digits, and since there's no sort of variation on these digits, or small variations, you probably can build a perfect classifier, which means the expected value is either 0 or 1. But it's not always the case. For example, if x represents a human-generated written digit and y indicates, again, if the digit is a 5 or any other digit, then f of x is somewhere in the interval between 0 and 1. So it is typically impossible to classify human-generated written digits perfectly. It might be very close to 1 if it's very certain that it's a 5 in this case, or it might be very close to 0 if it's pretty certain that it's not a 5. But for example, it could also be 1/2, which means it's completely uncertain about if it is a 5 or if it's not a 5. So this underlying function is sometimes called the true function, or the data generating function, or in engineering domain, sometimes the system you're trying to model. Sub W of x is a model with a parameter vector W, which is unknown, and W has MP components. So MP is the number of model parameters. And the goal is of learning is to find an estimate of W, also in this MP dimensional space, such that f of W hat of x is approximately, or is very close to the true f of x. And in supervised learning, we learn this estimate based on a training data set of size n. So we have in the training the input xi and the target yi, where n is the number of training data points. Okay, so here we see again the data matrix for supervised learning. So the bluish boxes on the left side are the inputs. Again, each row is a input data point. We have n of them, and we have m real inputs, and the number of parameters is, in this case, m plus 1, so mp is m plus 1. So data input is a row here, so we see what we denote by x2 transpose, so this vector over here. So this would be element third row and second column, second real column, and the last one is then x sub 3 comma m. And here on the right side we see what was measured for this input, the y3 in this case. And the goal is to make a good prediction for a new test data point, so one which was not in the training data. So for example, this is x transpose over here, and we were interested in predicting this reddish box here. So what is the new y for a new input? So this from this we want to get a model which is good at this. M is the number of inputs, m sub p is the number of free parameters, n is the number of training patterns. xi is the ith input, so it goes from I0 to IM. So it's the ith pattern with component 0 to m, and the xi0 is always 1. Transpose, so we typically write every vector as a column vector. Xij would be the jth component of training pattern I. X is the so-called design matrix, which is this bluish thing over here. So it's each row of X is a training data vector, but as a row vector. Whereas when X is alone, we typically use it as a column vector. So that's a little bit tricky to remember. Xi is the target for the ith pattern. Y fat is the, or bold y is the vector of all targets, also as a column vector. That's why we have the transposed here. Di is the ith data points, which includes the inputs and the target. Then D, big capital D, are the training data, so all the inputs with all the targets, so written as a set over here. X is a generic input, typically a test input. So there we don't use an index for X, and if it's an index, it's the component of X. It's also sometimes a little bit confusing. Y is the target for X, and Y hat is our best model estimate for FWX. Of course, Y in the application is unknown. If we leave some data to evaluate the test set performance, then we might also have Y scalar Y available for one or several data points. So the notation is, you have to pay attention a little bit. So bold x is a generic input, and xj is the jth component of x. Y is a generic output. Xi is the ith data point in the training data set, and Xij is its jth component, and Y sub I is the target associated with X sub I. The first column, so the first input, we assign index 0, so that's always 1 if we use it. So it's an auxiliary input. It's not really related to the information of the input. Y bold is the vector of all targets. And as discussed before, xi is a column vector, but it appears as a row in capital X. So that's just the convention. And for linear models, as we're considering now, the number of parameters is the number of inputs plus 1. And f sub wx is a model function with parameters w. W opt are, sometimes we call it w hat, are the optimal model parameters based on the training data according to some cost function. It might not be unique, and it might not be the true one, of course. F of x is a true but unknown function, which generated the data hypothetically. Sometimes, but not in general, the true function can be represented by one of the model functions. Then w sub true is are the parameters of that model. Sometimes this is not unique. So in this case, the f, if we substitute here for w, the w true, would exactly be the f of x. Also, there's an interesting difference to statistics. Of course, statistics has a lot to do with machine learning, but culturally it's a different field with different goals, but of course there's a huge overlap. And in classical statistics, one is often interested in the distance between the best parameter I get out of my training procedure and the true one. So this distance is of interest. In machine learning, one is often interested in the distance between the prediction of the optimal learned the model with the optimal parameters and the true model. So we are more interested in the test set performance, whereas here we are more interested in classical statistics in the that we find the correct and maybe interpretable parameters. Here's sort of a flow of information. We are often showing in one way or the other, and here I try to even motivate it a little bit from a biological perspective. One reason is that initially when I started giving this lecture, machine learning was not such a hot topic yet, and I tried to motivate as good as possible that machine learning is interesting. So also for historical reasons, the input is on the bottom. So this might be a vector of sensor data, for example, pixel in an image. Then we perform some pre-processing, which might calculate some information, some important features from the sensor data. Sometimes we are using the sensor data directly, but sometimes we do some feature calculation, some pre-processing. For example, we might decide on edges in the image. Then we have typically a very high-dimensional feature space. So this might be some layers in your cortex. And then we have a classifier. So everything converges to one output. For example, before we had the example 5 or not 5, and it might be mother or not mother. And this is how a large portion of machine learning actually works, at least until deep learning occurred. So we have some input data, we have some insights on what sensible pre-processing is. We generate a high-dimensional feature vector. Sometimes we do then some model reduction or some dimensionality reduction. And then we train a classifier on top. And the last classifier is often a linear classifier. And so today we are learning about this top part, the linear classifier. So here are some examples. A biological system might need to make a decision based on available sensor information. An OCR system classifies a handwritten digit, like in zip codes, or a forecasting system predicts tomorrow's energy consumption. So in supervised learning, which we are concerned about today, one assumes that in training, both the inputs and the outputs are available, and in testing, the model only knows X, and the goal is to predict Y. Of course, in real testing, we know the Y. We just took out some data from the data we had as test data, but in the use of the model, we don't have Y. We have only the patterns, and the system needs to decide on the zip code, so nobody tells it's a zip code. An input pattern might reflect the attributes of an object, and the target is the class membership of that object, cat or dog or human or whatever. The goal is the correct classification for a new input, for a new pattern. So that's important. I mean, in training, we are sort of trying to be good at the training data, but only in as much as it also gives us good performance on the test data. So sometimes you train a model and it gives you 0 training error, but the test error is not very good, and sometimes it's better to have a little bit error left on the training data, gives a better performance on the test data. A linear classifier is one of the simplest but surprisingly powerful classifiers, and it's particularly suitable when the number of inputs m is large, because then a linear classifier often separates the classes quite nicely. And if m is not large, one can transform the input data into a high-dimensional space by a preprocessing step, where then a linear classifier might be able to solve the problem. This is central to a large portion of the lecture, for example, lecture on basis functions, on neural networks, and on kernel models. And the linear classifier can be realized by a perceptron, a single formalized neurons. So if you look at this picture back, this is where the neuron, the perceptron is happening, and this is where the preprocessing or the basis function selection is happening. The perceptron was the first serious learning machine. It was invented in 1957 at the Cornell Aeronautical Laboratory by Frank Rosenblatt, and we already talked about it a little bit in the first lecture on the introduction. So this is how it works. So again, the inputs are represented here on the bottom. So often we draw these nodes, and we sort of apply or set these nodes to these values. So the first one is always 1, and then we have the real inputs, so the real values of the input pattern. We have m of them. Then we multiply these values with these numbers here, the so-called weights or parameters. So the first one is multiplied by W0, the second one by W1, and the last one by Wm. Then this H, which is shown over here also on the right, is simply a weighted sum of the inputs. And here you see this product, which I just described. And then H is just the sum of these weighted inputs. And this is sometimes called net input. Sometimes they call it activation. And in biology, it would correspond to the membrane potential. Then we have this transfer function here. It's called activation function. So in this case, it would be sign, which is, so if it's 0 or larger than 1, it transfers it into 1. If it's smaller than 0, so it's 0 or larger than 0, it transforms it into a 1. If it's negative, it transforms it into a -1. So it's shown over here. And our so this is our our best estimate after training. It's simply the sine of h of x. So this is how we make a prediction for nu in x, where we don't know the target yet. One feature which is interesting is where this h is 0. We'll discuss it shortly in more detail, because this defines the so-called separating hyperplane. Yeah, so in this discussion, f of x is simply the sine of this h of x. You might recognize that this is a very simple formalized neuron. Here are the inputs. Here the W's are the synaptic weights. And this would be the cell body, and this would be the output. And in this case, the output is either 0 or 1 for a given input pattern. It's important to visualize what is going on, and you can plot different things. So here we assume there's only one real input, so only x1, and here we plot the y dimension, the output dimension. And so the red is the output of our trained classifier. So in this region, when h of x is smaller than 0, the output is -1. So for these, here's 3 examples. Then at the location where y becomes positive, or h becomes positive, the output switches to 1, and this is the output of our perceptron. So in this case, all these data points are correctly classified, because here they had output value 1, here they had output value -1. And the function here is w0 plus w1 plus x1, so that's only one real input. If you input 0, then h is simply w0. So in this case, it's negative. So this blue one is the h curve, so h of x, and the red one is the y. So after applying this, the sine function, the y of x. And where is this point? So if you set this to 0, it means this point is located when this distance here is minus w0 divided by w1. And this is this famous separating hyperplane. In this case, it's a point because there's only one input. This is how it looks like in 2 dimensions. And now you have to pay attention. We are drawing the 2 inputs, x1 and x2. And the y, the output, would be sort of perpendicular, would go out of the plane here, which we're showing here. So here's the h function, so it's -3 plus 2x1 plus x2. And if we set this to 0, we get a curve for x1 as a function of x1, which is this one. So this is the so-called separating hyperplane, in this case a one-dimensional manifold. And everything to the right of this plane here, we classify everything as class 1 or plus, and to the left everything as class 0 or -1. Yeah, and if you go further away to the right, the h function increases. If you go further to the left, the h function becomes more and more negative. So this is how it's typically drawn in 2 dimensions. This is the separating hyperplane, and this is positive and negative. Here it's how you calculate it. You just set h to 0, and then you solve for x2. So x2 is 3 minus 2x1. So this is the separating hyperplane. And yeah, there are many things which are linear in the perceptron, and it's important to keep them apart. otherwise you get confused. So h of x is a linear function, so h is a linear function of x. So with m equals 1, h is w naught plus w1x. With m equals 2, h is w naught plus w1x1 plus w2x2. And the other linear thing is the linear hyperplane. So if you set h of x to 0, then the linear hyperplane is also defined in 2 dimensions, at least by a linear line or one-dimensional manifold. So h of x equals w naught plus w1x plus w2x2. If you set it to 0, you get x2 as a function of x1, and graphically it also looks like a linear line. So these are two things which are linear, and sometimes it's a bit confusing. You have to pay attention what is being talked about. One way to look at the perceptron, we said that it's an important or powerful classifier if the number of inputs is very large. And for example, if you consider that the input here can only be 0 and 1, then if the input is 0, it doesn't have an effect on h. But if the input is 1, sort of the influence on h is w. So the magnitude of w you might consider the strength of the input, of this the importance of this input, and it votes for an output of the sign of this w with this weight. So if, in other words, if let's say we have only binary inputs, and if w is very large in magnitude, it has a lot of influence. And so in this wiew, you can think of it almost like a voting machine. Some inputs then vote for plus, and some inputs vote for minus, and the w's, the magnitude of the w's would be the strength of their vote. So that maybe explains a bit better why these linear classifiers are already quite powerful, although they are so simple. Now, if you think of it as a voting machine, and in high dimensions, it can be quite a meaningful classifier. So now we know how the perceptron functions. And now, of course, the question is, how do we find the optimal parameters or weights, W0 to Wm? So we define a cost function, also called loss function or objective function, that is dependent on the training data and the parameters. So with the model structure fixed, everything then becomes, and the training data is also fixed, a function of W, of the weight vector. And in training, we are trying to find the parameters that minimize the cost, which is defined on the training data. And this is our best estimate of W. So it's called a point estimate. We are really committing then to one solution. So we want to minimize this cost function. So the goal is correct classification on the training samples with target y1 to yn, and the perceptron cost function assumes this form. So it's a negative of a sum over all currently misclassified patterns. So with a certain parameter vector w, some training patterns will be correctly classified already, and we don't care about them. We only care about them which are incorrectly classified. And the cost is the product of the true output in the training data, so the yi, multiplied by the h of xi. Um, so obviously they must have different signs. If they would have the same sign, then they would not be misclassified. Um, and so this is a negative value. Negative is positive. So it contributes as a positive term to the cost function. You can also write it as a sum over all training data if you consider this function which returns the argument, so the input or 0, whatever is larger. So again, here the the correctly classified patterns drop out of the cost function because they would be in this range, and the um, misclassified get this minus yh contribution to the cost function. And here h of x is the sum of the inputs. We already know that. And the cost is 0 because this can only be positive when all patterns are correctly classified. Also then this set of misclassified patterns becomes 0. Otherwise the cost is larger than 0 because yi and h of xi must have different signs. So I can also plot it in this way, this product YH. So if they have the same sign, it's a correct classified pattern and there's no contribution to the cost function. And if they have different signs, then the contribution to the cost function is linear in the magnitude of H. So the very popular way of optimizing this cost function, which is also called learning, is gradient descent. So you start the algorithm by initializing the parameters typically with small random values. And then you want to change in each learning step the parameters such that the cost function likely decreases. And the idea between gradient descent is to adapt the parameters in the direction of the negative gradient. So here is an example. It's not exactly the way the cost function for the perceptron looks like, but it serves as an illustration. So this red curve here is the cost function, and the input is the parameters. So it's not x, it's the parameters. And maybe you start your training here on the left, and then you want to move in the direction where this cost function gets smaller. So in the next step, you end up maybe here on the second point, and then at the end, you find the optimal parameter here, which minimizes the cost function. So what we need is to find the direction of the negative gradient here. The positive gradient would go in this direction, negative gradient goes in this direction. And so we start with our cost function and substitute the linear term here for the h part. And then we take the first derivative of this cost function with respect to wj. So wj is just one component of the w vector. So we have the negative, we have the sum over all misclassified examples. And if you look at this product here, if you take the derivative with respect to w, the w drops out of the equation, and you're left with xij times yi. So this means if you have ax and you take the derivative with respect to x, you're left with a. So that's the same rule here. And so the cost is the sum over all misclassified patterns, yi times the corresponding input, which belongs to the component wj. So a sensible adaptation rule would be that for all wj's, so this means this is the new w, is the old one, plus some small number, eta, so 0.1, 0.1 or so, that's called the learning rate, times this expression. And since this is already negative, it becomes positive here, because we want to go in the direction of the negative gradient. Yeah, so this is what we already discussed. So this is how it looks like in 2 dimensions, also a little bit idealized. So we have W1 and W2, and we start with W vector here, and then in each step we are going. So these are this is a cost function, and these are equal height curves of the cost functions. So W goes locally in the direction where the cost function becomes smaller, and then when we are lucky, it will end up here in the optimum. So this would be the minimum of this reddish cost function, and this is how it goes. No? So we start here and we find the optimum of the cost function. That's how our learning procedure works. The actual learning rule is a stochastic learning rule. It's called stochastic gradient descent, and it has several advantages. For example, it's faster, and it's also not so sensitive to bad solutions. We'll come to this in a moment. Also, it's biologically more plausible. The brain doesn't first accumulate an error and then adapt something. It does it for each training data input. So here we now use the index t to indicate that there's some temporal sequence of training data points. Before it was xi, now it's xt. So at time step t, we are optimizing wj in the direction of the negative gradient, but calculated only on this actual training data pattern at time t. So the difference is here. Here we had the sum, and here we don't have the sum. And of course, if the training data point is correctly classified, we don't do anything because there's no gradient, and only if it's misclassified, we apply this gradient rule. So in this rule, a weight increases, which is a synaptic weight, when postsynaptic y, so the output is 1 or minus 1, and presynaptic x have the same sign. And this sounds like Hebb's rule. No? So correlation implies strengthening of the synaptic weight. So that's part of why people got excited about this learning rule, because it seems to implement Hebb's learning rule. And if the signs are differ, then it will decrease the synaptic strength. But don't take it too literally. It's more like some interesting connection. Of course, some of the things which are going on in the perceptron learning rule might not be so biologically plausible. Eta is larger than 0 is a learning rate, typically between 0 and 1. And this learning rule is called stochastic, or it's an instance of stochastic gradient descent. Gradient descent we know is stochastic because you apply in random order maybe the axis, and then the random order in which you present the axis determines also the way this model is optimized. So it's also it's not in this sense it's not a deterministic learning rule. So we look at the figure before, and now we see sort of a similar behavior, but the adaptation steps are a little bit random. I mean, the trend is sort of correct, but because they don't really see the true gradient, they always only see an approximation to the gradient based on one training data point. The actual adaptation will have a little bit more stochastic behavior. But it will also, let's say, find the correct solution. There's a convergence proof with sufficiently small learning rate eta, and when the problem is linearly separable, the algorithm converges and terminates after a finite number of steps. But if classes are not linearly separable, then there's no convergence. And that's also a big problem. We'll come to this in a moment. So here, just to illustrate what's going on, so here's the current decision boundary. On this side, it's positive. Here it's so it's 1. It's -1, and this this data point has target 1, but it's in the -1 region. It has coordinates 2 and 1. And h at this location is -1 if currently we have this h function 0 minus x1 plus x2. That's why this is a separating hyperplane. So the separating hyperplane prior to adaptation is x2 equals x1, which is this curve here. So the 0 is the current value here, then plus learning rate times, and now the output 1 times the input, which belongs to W0, which is the constant input, so it's also 1. So the new W1 will be 0.1. And then W1 was -1 plus eta times, and then again the input here is 2, and the target is 1, so here we get a -0.8, and for W2 it's 1, that's this one here, plus 0.1 plus 1 plus times 1 equals 1.1. So after adaptation, we have this h function, 0.1 times 1, so this changed from 0 to 0.1. Then minus 0.8 times x1, it changed from -1 to -0.8, and plus 1 became plus 1.1 times x2. Then the separating hyperplane is defined by this function, minus 0.09 plus 0.72 times x1. So it moved a little bit in the direction of getting closer to this incorrectly classified data point, and if you do this gradient steps a few times, eventually it will move to the right side of this data point. So what are these linearly separable classes? It means there's a solution which completely separates the training data. So here's one class, the red circles, and the green crosses are the other class, and here's a separating hyperplane, and these two data point sets can be perfectly separated. So this is x1, x2 space again. And in this case, we can find a solution. So here, this is prior, the orange curve, separating hyperplane, is before the adaptation, and then after the adaptation, it might generate this blue line or this blue line, depending on what training data it is using to minimize the training data, to minimize the cost function, assuming there are different ones. I guess here's only one. And so it will end here because all the training data is correctly separated. But this also shows a little bit the stochasticity, depending on what the last data, the data point was, which brought it to this correct solution. It will find slightly different separating hyperplane. So the solution is not unique. So this is an example of data distribution which is not linearly separable, because you cannot find a hyperplane here, this bluish line, which can separate these two classes. So this is how the plus class is distributed. This is how the reddish class is separated, and no matter how you draw a line, it's impossible to separate. And this is the classical XOR problem. So you have plus and minus. And so there are 4 data points which cannot be separated by a linearly separating hyperplane. And this was a famous example which was used in the book Perceptron by Minsky and Papa to show the limitations of the perceptron. And it's true, you cannot do this, but one would argue in high dimension, this is not very likely that this happens. And also, of course, we use more than one neuron now, so we have much more powerful classifiers at hand. But this was sort of supposed to be, at least that's how the story goes, the example which broke the perceptron's neck, if you want. And unfortunately, the perceptron doesn't even behave very nicely if the classes cannot be separated. So for misclassified data points, it tries to get the magnitude of H to be small, because at least then the contribution to the cost function is small. But this means that the length of W becomes small, and then learning tends to become unstable. So it's not even not separating, it's also not really terminating the learning. Okay, now we show some examples how this behaves. So the first example is the OR, which can be separated linearly. It's linearly separable. And so this is the separating hyperplane. It is learning. So here this is classified as -1, and everything to the right is classified as 1. So this is a starting point. This is not the solution. I was a little bit confused here. But these are the targets, no? 1, 1, 1, -1, and any separating hyperplane. For example, this one would separate these two classes. This is how the adaptation of the W's looks like. For example, this one starts here at the negative value, then increases a bit and then stops. And the other ones also behave quite nicely. Here the error is 0, and then no adaptation is going on anymore. The cost function decreases nicely and then hits 0 and stays at 0. And the number of misclassifications sort of jiggles around. I guess there are 4 data points here, and then becomes 0 and stays 0. So this is the beautiful behavior, the learning behavior of the perceptron for separating, for classes which can be linearly separated. Here's the XOR, so we have 1 and 1 here, and -1 here, so we cannot separate it. And if you look at the W's, in fact, their values get pretty close to 0. And depending on the learning rate eta, they jiggle around at 0. The cost sort of decreases, but then it never really becomes 0. It becomes small because the H becomes small. And if you look at the number of misclassifications, it's also non-stable. It never goes to 0 because it cannot be separated. And you see this sort of unstable behavior quite nicely. So with separable classes, convergence can be fast. That's nice. A linear classifier is a very important basic building block in more complicated systems. because one can argue that if the number of inputs approaches infinite under some conditions, most problems become linearly separable. Sometimes the inputs are already very high dimensional. For example, a text might be classified by the occurrence or non-occurrence of 10,000 keywords. In this case, a linear classifier can already do a good job to classify a text into whatever, sports, literature, whatever. And in other cases, one often first transforms the input data into a high-dimensional space, sometimes even infinite space, when we use kernel systems, and then we apply a linear classifier in that space. And that's the basic idea between basis function approaches, the kernel trick, and also neural networks. Also consider if you how powerful a single neuron is, and the brain is high-dimensional. Typically, a neuron has 1,000 or 10,000 inputs. How much computational power can 100 billion neurons really possess? So this is really one neuron only. Sometimes a single neuron, if it classifies cat or non-cat or grandmother or non-grandmother, is called a grandmother cell. So one neuron might be responsible for one particular item in your world. The learning wheel itself is not much used anymore because of these convergence problems. And even if the classification boundary, if the classes can be separated, the solution is not unique. So the optimal W is not unique. There are many Ws which separate the classes in case they are linearly separable. And we will learn about alternative learning rules like the support vector machine, the linear support vector machine, or the optimal separating hyperplanes, the same thing, Fisher linear discriminant, or logistic regression. So yeah, these are some details on the geometric relationships. So we can, the separating lighter hyperplane can be written as this, x transpose w equals 0, no, because this is just a weighted sum of inputs, or x tilde transpose w transpose tilde equals minus w naught. So here we are only considering the real inputs and the weights on the real inputs, and not the weights on the one. Then we can define this unit vector, which goes in the direction of the w, but so normalized to length 1. And we see where this w, or this e tilde vector, the unit vector, hits the separating hyperplane at this point, minus w naught divided by the length of w tilde times e tilde. So that's shown over here. So this is separating hyperplane. This is e tilde, which is perpendicular to the hyperplane, and the distance between 0 and the point where it hits the hyperplane is magnitude w divided by the length of the vector. Yeah, I particularly like this application, which shows you the power of a linear classifier. So this is a brain, and these are patterns which people find in the activation patterns, which they find by fMRI technology, and these are, in these cases, the subject is listening to or thinking about different terms. And they use these pixel images to classify what the person is thinking about. So a trained linear classifier was 90% correct and can predict if somebody reads about tools or buildings, so can make this separation with 90% confidence. Oh yeah, the figure shows the voxels which were most important for this classification task. Typically, if you're thinking about terms, your language areas become active, but also the areas which are associated with the object, like a tool, a hammering, the sound of hammering, the movement becomes activated. And so we are now here in this application, we have high dimensional pixel values and we can directly classify it. In other cases, as we discussed, you want to do this pre-processing step. Finally, what is this? Why does this pattern recognition work so well? Why does a linear classifier classification at all is so powerful? Because maybe from intuition you would think the world can be described by logical rules, for example. So von Neumann put it in this way: the brain uses a peculiar statistical language, unlike that employed in operation of man-made computers. And classification problem or machine learning typically looks at a high-dimensional input vector and doesn't do logical decisions based on them. It trains a classifier. So as we discussed already, in the perceptron can be looked at as a voting. And the voting is sort of robust against problems with one input if the other inputs are correct. Because then a single input has little influence on the classification boundary. Yeah, the alternative is try to learn simple rules to solve the task. And it's still maybe a little bit of a mystery why these pattern-based methods work so well and rule-based approaches don't, at least not yet, work so well, despite the fact that when we explain a decision, we are typically trying to explain it by saying, oh, but look at this rule and this is the explanation. In technical, these rules are either trivial or known or extremely complex and very difficult to interpret. So if you try to learn these rules from data, it's not so successful so far. But this is a little bit counterintuition, whereas, for example, this might be a rule we might communicate as humans, which people are often interested in buying a yacht unless they already own one. Also, computer programs, machines follow often these simple rules. So why is it not working so well in learning? One problem are exceptions. So what birds fly? So do birds really fly? First, you have to define what is flying. That's so obvious. Now, using your own force, a distance of at least 20 meters, maybe, at least 1 meter high, at least once every day in its adult life. Otherwise, it would maybe not be considered flying, at least not autonomous flying. And birds can fly, but not if they are penguin, or if they're injured, or if they're dead, or if they're too old, or they don't fly if the wings have been clipped, or if they have a number of diseases, or if it only lives in a cage, it probably doesn't fly. If it carries heavy weight, it might not fly. So there are many reasons why a bird does not fly. And specifying all these details in terms of rules is very complicated, very cumbersome. There are not too many people who can give you these rules, and learning these rules seems not to work so well yet. So, of course, pattern recognition has no problem with saying that 90% of all birds fly. So it doesn't care about details, maybe. But if you have more input information about the actual bird in front of you, you can be better in the accuracy. So all birds which do not belong to flightless class, 94% fly, so it's already more. If they're not domesticated, the number even goes up. So it's one problem is the complexity of the underlying maybe deterministic system, and then of course another problem is incomplete information. So here we can make the statement even with incomplete information about the bird, whereas a logical system which would be very difficult to make a statement here at all. And this is sort of the success of the reason why statistical learning is so powerful. So here's an example. Rich people are often interested in buying a yacht unless they already own one. So we can maybe we can collect information about the person, for example, the wealth, and then estimate the probability of buying a yacht given the wealth of the person. But maybe we don't know that parameter. Let's look at the picture. I think that's easier to see. So, so if we know the wealth of a person, we can predict the probability that this person is interested in buying a yacht. And maybe we say, okay, there's no other real important input, and the wealth of the person can be can have effect on other things. So maybe you cannot measure the wealth directly, but you might know what car the person owns, if he has an expensive home, if he does a lot of overseas vacation. So in the case that we don't have this information, uh, the wealth, maybe we build a model to predict the wealth from some past data. If we have the wealth, then we know, okay, what is interested in buying a yacht. But maybe we cannot get wealth data at all, or maybe we don't even know that this wealth variable exists. So then maybe we do a direct model. We get data on people who bought yachts and what their properties are. So what car they drove, if they have an expensive home, if they do a lot of overseas vacations. And without this variable, which might make the dependency very low dimensional and explainable from income to yacht, we now have a lot of inputs, which might give you quite a good prediction on the interest of a person buying a yacht, but it's very difficult to explain because all these things maybe make some small contribution, and only in the overall pattern we can decide where the decision boundary really is. So maybe this gives you a little bit of intuition why pattern-based learning is so powerful, whereas like low-dimensional rule-based learning often doesn't work so well. Also recall that Pavlov's dog was really a prediction problem. The dog eventually learned to associate the bell with expected food. He didn't know the true cause necessarily because he didn't have complete information. He had to work with the information which was available, which was the ringing of the bell, and then he could predict that there was some food available. So as a conclusion, one reason why dependencies tend to be high-dimensional and statistical in nature is that the input of interest, here the wealth is not available, cannot be measured, and these sometimes they're called latent variables or hidden variables, and latent variable models try to estimate this latent variable, and then we can apply our low-dimensional rule. So sometimes people use methods like PCA or clustering. But sometimes this is not suitable, and we directly try to work with the available data. So exceptions are an important problem. No? So in technical human-generated worlds, sometimes rule-based approaches work quite well because the products were manufactured under strict rules. For example, engine A always goes with transmission B. This is very simple, can be translated into rule, and there are no exceptions. So there it works. But or tax forms, no? That also seems to be a legal system. But the fine-tuned text system, of course, becomes quite detailed. So it's not a simple form, typically, simple text form. Or natural laws under idealized conditions, without friction, without wind, also follow low-dimensional dependencies. Yeah, and also language seems to be happening more on the deterministic setting, but there's some reason to believe that also humans don't necessarily use these rules for making a decision, but more for arguing than for the decision or justifying the decision. It's not because, oh, I feel like I should go to Italy. Maybe that's a pattern recognition problem. It's more like, oh, we will go to Italy because it has the best beaches, which is a simple rule again. But it's not clear that how often we really follow these rules. So the last slide is another form of the learning rule. It's the same one. We don't have to make this distinction between misclassified or classified. We don't have this this linear curve with this, which is 0 on one side, but it's exactly doing the same thing because so WT minus estimate WT, of course, it's 0 if we have if the classifier and the data agree. So it also drops out if the classes agree, and in the non-agreeing class we get the desired learning rule. So formally it looks like a so-called Adeline learning rule, which we'll learn about later. It's the same thing, so if you prefer this form, it's also okay. Okay, thank you very much. This was the lecture on the perceptron.